Okay, so once you got the histogram done, we are now going to answer several questions about the histogram and about our data. So basically, we are going to answer D, and then we're going to go through all of this stuff. So I would recommend you trying to do it first on your own, but I'm going to go through how to do these, okay? So is the data normally distributed? So again, normally distributed is that this should be a nice bell-shaped curve, all right? So no, it is not, all right? Maybe if this had a few more bits of data here, you could argue. So it's not bell-shaped. Now, could it be if there was more data? Yes. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's very difficult to make a histogram with only 12 bits of data. If we had 1,200 bits of data, it might end up being bell-shaped. All right, so now we have some, we're using the mean and the standard deviation to make predictions. All right, so for some of these, we're literally just writing things down. So calculate each of the following, round answer to the thousandth of a centimeter. So this is asking for the mean plus the standard deviation. So for us, we're probably just going to go to the tenths. All right, so the mean, what I got for the mean was 4.1. So 4.1, and my standard deviation was 0.2, so 4.1 plus 0.2. So this is 4.3. So subtraction, 4.1 minus 0.2 equals 3.9. All right, and then this is asking for 2 times the standard deviation, so 4.1 plus 0.4, all right, which is 4.5. And this one is 4.1 minus 0.4, which is 3.7. Okay, so that's somewhat simple. It's basically just doing a little bit of math. All right, write an inequality that represents all of the data values that fall between the values of mu plus or minus just the standard deviation. So an inequality basically means that we would take this value and this value and kind of put x in between. So 3.9, and then if we wrote x is in between, so using that greater than sign, and then we would put in 4.3. So basically we're saying that all our data falls between 3.9 and 4.3 if it's within one standard deviation. All right, so theoretically, if the data is normally distributed, what percentage of the sample should fall within one standard deviation? All right, that's from our notes. You should go check. And you should have seen that it should be 68%. All right, so now it's asking what percentage of the data falls within the limits. All right, now how could we figure that out? Well, we would look at our data right here, and we would see how many of them would fit within 3.9 to 4.3. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 10 bits of data fall within that. So what we would do is we would take 10 divided by 12, which is the total amount of data, and 10 divided by 12, if we do that math, is 83%. All right, so it's greater than 68%. All right, so what percentage falls within? All right, show your work. Does this agree with the theoretical percentage? No. All right, greater than 68%. Okay, write an inequality that represents all the data that fall between the values of 2 times the standard deviation. So similar to up here, but instead we're using these two numbers. So 3.7 greater than or equal to x greater than or equal to 4.5. All right. So theoretically, if the data is normally distributed, what percentage should fall within that? All right. So if we look, that should be 95% based on our notes. Okay. Now, what percentage of the data falls within that? So if we look right here, we know that these 10 bits of data already fit within there. Does 3.8 fit? Yes. Does 4.4 fit? Yes. So we have 12 out of 12 bits of data fall within that, so 100%. So no, it's greater than 95%. All right, so that's how we do that stuff. You are now going to do it with your own data. All right, so very similar to what we just did with data I gave to you, but now you're going to do it on your own.